actually, for someone who's not seen a LIGO talk before, just a little discussion that sort of to give you a foundation. So what I'm going to try to go through is right here. I'm going to give a little deeper introduction on gravitational waves and try to get across actually what's waving. That's maybe the hardest thing to wrap your head around, is when we say we've seen a gravitational wave, this exotic wave that Einstein predicted in 1916, what's really going on? What's really waving? So I'll try to spend a few more slides on that than I normally did in the past talks. And then I'll update you on what's really our third observation run. LIGO as a project was proposed in the 80s. It was funded, all told, it's about 1.1 billion in investment that led to the first detection of gravitational waves in history in 2015. That ultimately yielded the Nobel Prize in Physics in 2017 for the founders of the project. And that was in our first observation run. 2017 was our second observation run, where, on Floyd's birthday, we discovered gravitational waves from 2 neutron stars. And then we made our third observation run in 2019 and a bit of 2020. It was preempted a bit 1 month early by COVID. So I'll give you a little rundown on that. And then I'll try to tell you what's going on now. And then Frank sent me a whole bunch of great questions, which we won't have time for all of them. And he just added one because the power and the detection wasn't there for it. So we can talk about some of those. And I'd say if you have a question and you want to break something loose in your talk, just unmute and fire away, because I know the way I learn, I have to ask questions as I go. So I would be happy to stop and take a question in the middle of the talk, or you can save them for your end as you choose. Okay. So I'm going to start by telling you what it is we're looking for. What is the gravitational wave? In particular, when we think of the vacuum of space as nothing, right? It's not really nothing, it turns out. It's quite an exotic, complicated object mathematically. But let's think of it as nothing, empty space between galaxies. Then what could possibly be waving? Turns out the answer is space and time itself. So I'm going to use this little balloon image to describe the expansion of the universe and try to convince you that, the space itself is kind of a malleable object, more like a sheet of rubber than nothingness. So you might have heard from the opening of the Big Bang Theory show that the universe starts in this hot, dense state, and then all matter is sort of separating over time. And what you don't want to think about when you think about the origin of the universe in a Big Bang, you don't want to think of it as a bomb going off into pre-existing void. It's the void that's getting created all the time. And so we model this in this little diagram by drawing galaxies on a 2-dimensional universe. We're going to simplify our universe, just longitude and latitude on this balloon, and draw some galaxies there. And then we'll fill that balloon with air. And then if you're sitting on one of those galaxies looking through just the 2-dimensional surface of the balloon, you would see those galaxies all receding away from you. And there's more space in that universe over time because the balloon is somehow expanding. So it's getting stretched. And that's completely analogous to the way our 3-dimensional universe is, in that after a moment of incredibly high density and energy, space itself is expanding. There are more places to go in the universe than when we first sat down for our meeting some 37 minutes ago. So that is an effort to give you a sense that, wow, space and time are these more exotic objects that have properties. They really can stretch and expand and contract. So if we accept that, we can also think, what if I had a violent event on the surface of that balloon, like 2 black holes in the 2-dimensional surface colliding together? That might you can think of thwacking the balloon with your finger, and that would send out a ripple that would propagate and wave dynamically and race around the balloon and bathe the entire universe, getting weaker and weaker as it goes. That's really that dynamical property, the waving of space and time, because it shudders in recoil due to some violent event like 2 black holes colliding or the birth of the universe in the Big Bang. Those types of events create gravitational waves which propagate around the universe. That's a lot to take in. And
Michael, let me ask you, these 3 balloons, do they represent the entirety of the universe, of space?
That's a great question. In this model, yes, they do. But that's a model. The universe here is finite. There's a finite number of galaxies, a finite amount of space in the universe. If you were sitting at the galaxy in this right-hand picture, the spiral galaxy in the bottom left of the right-hand balloon, if you went in some direction, ultimately you'd come back. You've traveled the straightest line possible. You know nothing about the curvature of that space. You'd end up right back where you started, right? Without, just kind of like we do on the surface of the Earth. If it looks flat to some people on the internet, people think it's flat. If you travel in one direction, you end up right back where you are. That is a model. That is a possibility. It's an unlikely thing in our universe that, in principle, if you flew off in a rocket, you'd end up right back here, despite traveling the most perfect straight line you possibly could in the space. So that's what's called a finite but unbounded universe. You don't come to any edge, but there's a finite number of places you go. You can also think of this as some sort of saddle or curved sheet or something like that goes on infinitely, and it's an infinite and unbounded universe. Both models work. Both models are acceptable. The infinite and unbounded one is favored by data. Okay, so the whole point of this was to convince you that space has some properties that are unexpected and can stretch. And if we thwack that balloon, that ripple makes gravity. As it propagates, it causes these tiny fluctuations. Now, in this slide, we're going to talk about another property that Einstein thought gravity should have, and that's that it travels at a finite speed. You might have taken Newton's theory of gravity in high school or university, and that tells us how gravity, creates orbits for planets and creates our solar system, creates the collapse of gravity and formation of galaxies. All those things are bound up in Newton's theory of gravity. It's really good, but it doesn't tell you how gravity moves from point A to point B, and it says it travels at an infinite speed, and nothing we know in the universe travels that way. So in this example, we've got gravity binding the Earth in an orbit to the sun, and we're going to vanish the sun instantaneously. We're not forming a black hole. We're just doing this thought experiment where what if the sun vanished? And so here the Earth is going around in its orbit and the sun vanishes. And if Newton's theory of gravity is right, the moment the sun vanishes, the Earth will propagate at a tangent off to the left here because the sun is gone. But if gravity takes a finite time to get there, then the Earth will continue on a curved path, even though the sun's gone, and then finally travel that tangent. That's the difference between gravity having a finite speed and gravity acting instantaneously. Einstein solved this gravity problem by making his general theory of relativity, like Floyd said, finishing it in 1915, making the first prediction for gravitational waves in 1916, where bodies like two neutron stars revolving around each other churn up space in an invisible way and make these ripples that are on the z-axis here. They're strong near the objects. They're weaker and weaker as you propagate away. And they're traveling in all different directions. We're just taking a slice out of the plane of the two stars here. And those gravitational waves are the force carrier for gravity that Einstein predicted. And they cause tiny disturbances in lengths. And so Einstein predicted this in 1916. And in 1970, people like Ray Weiss and others predicted how we could measure those tiny vibrations. And that's to shoot a laser down two long arms. And if the arms expand or contract because of these ripples in space and time, we can measure and read out the difference. So here's light waves, a laser passing through a 50-50 splitter, light bouncing off of one mirror at one arm and bouncing off the other, light combining back at the beam splitter, and then light is canceling here. So this output port is dark right now. Light's a wave and it cancels and adds the way waves do. And so if arm lengths change, that leaks a little light through and it lands on photodiodes in our detectors, and we're able to read that out. And that is the signature that the arm lengths have changed. We have multiple detectors around the world. We have 2 LIGOs, LIGO Hanford in Richland, LIGO Livingston in Louisiana, and together their arms, if they're kind of waving around doing the same thing, we can begin to argue that, this source is astrophysical. We also work with Virgo, a separate project, but we collaborate together in Pisa, and these other 2 detectors at LIGO India and Kagra are coming online. So those L-shaped detectors, each 2.5 miles long, each arm is 2.5 miles in LIGO. I'm just going to skip to these actual detectors. You can see LIGO Hanford here, LIGO Livingston in the forest, Louisiana, Virgo, which is a little shorter, 3 kilometers, and Kagra underground, also a 3-kilometer detector. They work in unison and search for these tiny modulations. The signal is so tiny when we, detect that 2 black holes a billion light years away have merged, they shrink our arms and expand our arms alternately by about 1/1000th the size of a proton. So extraordinarily tiny signal, 10 to the minus 18 meters or so. Okay, so we made our first and second observation runs in 2015, 2017. We ran our third observation largely in 2019. We shut down a month early in March, in the end of March in 2020, owing to COVID-19. And to date, we've noted that we have something on the order of 56 gravitational wave candidates, mergers of black holes, mergers of neutron stars, and potentially black hole eating neutron star events. That's the little artist's conception of a black hole tearing apart a neutron star as it falls in on the right. And so this original shot that I showed you was a publication that we've just put out, our latest gravitational wave catalog, in which we give 39 new gravitational wave signals from the first half of the third observation run. So that's really from April to October in 2019. And those are all depicted, many of them in blue here, as 2 black holes revolving around each other and smashing together and giving off energy in the form of gravitational waves and making a bigger black hole. So if you look at any one of these pairs of black holes, blue black holes, they merge to a heavier black hole. Same thing with the neutron stars in brown. Those are LIGO, Virgo neutron stars that have merged together to form what we don't actually know. Those gray objects in the center here include some neutron stars that may have merged to heavy neutron stars or to light black holes. We're not totally sure. And then also shown is what electromagnetic astronomers who use lights, visible light, gamma rays, X-rays, radio waves, infrared, have found in the universe in terms of neutron stars. So those are yellow, and black holes in purple. So if you compare LIGO stuff to what's known in electromagnetics, you find that we're on the heavy side. There's this whole population of black holes that no one knew about, and they were discovered by LIGO. So we're learning. You don't want to just find one object or 2 objects. You want to learn and do population studies to solve problems in astrophysics. Like, just take one of those pairings that merged. Gravitational wave 2019. So this is May 21st, 2019. We detected the heaviest gravitational wave black hole system that anyone's observed. It was a black hole 85 times the mass of the sun. That's what this little M dot symbol means. 85 times the mass of the sun, merging with a black hole 66 times the mass of the sun, and producing a big whopping 140 times, 150 times the mass of the sun, the remnant black hole. And according to astrophysicists, none of those objects should exist. You can do.
So where is the mass, the extra mass? That's 142 is not the sum total of 85 and 66.
Exactly. So you asked about power. And what's happening there is 9 times the mass of the sun is being converted in about 1/10 of a second to gravitational wave energy, into these distortions in the shape of space and time. And so this particular object here is the most powerful, most energy converted per unit time astrophysical object ever witnessed in the history of human beings. And because 9 times the mass of the sun were converted into gravitational waves in about 1/10 of a second. None of this is coming out in light. It's all coming out as these distortions in the shape of space. And if you were to say compare that to visible light, that is more power than if you summed up every star in the universe, the visible universe, and shone it for 1/10 of a second. So these are just wildly exotic systems. And the only way you can detect them is by finding gravitational waves with these gravitational wave detectors.
What are the efforts to detect dark matter through this process?
So that's a good question. Let me touch on that at the end. I have your questions down, Floyd, and I have the dark matter question. So let me hit that one at the end. Clearly those types of black holes are part of the dark matter, a small percentage, we think. So let me close in just a couple of minutes to touch on what we're doing now. So we're upgrading our detectors. This is a much smaller upgrade than the 200 million that Floyd noted. That was the so-called advanced LIGO upgrade to make second generation instruments. This is about a $30 million effort, which includes a third of that from UK sources. So right now we're in the midst of finalizing plans for this so you can see this main beam line here with the arms that stretch out 2.5 miles to the right. This chamber here houses our beam splitter, which splits the light. But we're adding something called a filter cavity, which is for a specially prepared quantum state of light called squeeze light. That one's about 300 meters long, so 0.3 of a kilometer. And so we've set this chamber, we're getting the beam tubes, we're building a small building outside, we have to punch through a wall. So this is a major change in the way we do business at LIGO. So that's a big element of many upgrades that we're doing right now. And the other one I wanted to flag is that these optics, while they're the most pristine fused silica optics on the planet, they cost about $250,000 a piece, and they still have tiny defects on them that are some form of tiny flecks of metal that are embedded in the optic in the preparation process at the manufacturer in LMA in France. So we're swapping out that optic. So I'm just going to show you a couple of slides because this is just from this week. Our team is in chamber with bunny suits on. That's to protect the pristine optics and the interior space of the detector from dust, particulate, hair, skin follicles, those sorts of things. And so this is an optic with the spot on it, a tiny, tiny spot, like on the order of microns across. That is coming out of the optic, out of the chamber here. And you can better see that this is one of our pristine mirrors here. It's now been put to this transport, and it's actually best seen here as it gets a quick inspection and then moves to its own isolated clean room. So that mirror, when gravitational waves change the length of the arms, that mirror acts like a survey stake in one arm to detect these tiny, tiny motions. That mirror gets stabilized to being, if you measured the ground noise with a seismometer and you and I can't feel any motion beneath our feet on which we're standing, if you measured that motion, that mirror has to become 10 billion times more still than the ground that you can't even feel shaking in order for us to measure this gravitational wave. So that face of that mirror is moving 10 billion times less than the ground you stand on here in Richland. Okay, last item I want to show you is that the Washington State has given us $7.7 million to construct an outreach center, the LIGO Exploration Center. This is one of the architectural drawings from Terrence Thornhill Architect here in Richland, Washington. And we are underway on construction. We broke ground on October 1. Here's myself and Amber Strunk, our outreach lead, Tim Doya and Terrence Thornhill from DGR Grant and Thornhill Architecture, respectively. Breaking ground, you can see the leveling that's going on here. Grand opening, March 2022. Please come out and join us. The center is for everyone, emphasis on K-12, college, university education, public outreach, teacher, professional development, the whole gamut, docent programs, everything. And that's what I wanted to tell you. I'm going to close on some of Frank's questions, but maybe first I'll ask, do folks have burning questions they want to ask him?